So we are doing 3.2 Rolle's theorem and the mean value theorem. So we'll start off with Rolle's theorem. Rolle's theorem says let f be continuous on a closed interval AB and differentiable on the open interval AB. Okay, so closed interval meaning the endpoints are included, open interval means they're not included. So that means if the endpoints aren't differentiable, that's okay. It's as long as it's a differential in between. If my endpoints, when I plug them in, are equivalent, okay, so like I plug in A and I plug in B and those values are the same. So I kind of picture a parabola, like when I plug in 1 and I plug in -1 into x squared, they're going to give me the same output. So at that instance, if f of A equals f of B, then there's at least one number C somewhere inside that domain, A and B, such that the first derivative of that value is equal to 0. So in other words, this is saying that there is going to be a curve of some sort. So let's just say something like this, okay? And say this is my ordered pair A, comma, f of A. And this is my ordered pair B, comma, f of B, and they have the same height, if you notice. So this would equal this because they're going to be exactly the same y values, okay? There has to be some value C, some x value C. So this ordered pair would be C, f of C. But it's in such a place that the tangent line would be horizontal, meaning that at this place here, f prime of C is equal to 0. So you have a horizontal tangent. So anytime your derivative is equal to 0, you're going to have a horizontal tangent. That's what it's asking. What it's implying is there's some sort of max or min, even if we reverse this, turn upside down, if you could have this happen such that this happens, then it's leading you towards a max or a min situation, okay? Maximums and minimums happen when your first derivative is equal to 0, which is why in that previous section we did that process. Okay, find the two x-intercepts of this and then show that f prime of x equals 0 at some point in between them. Okay, so in order for a value to be an x-intercept means the y value is 0. So we are going to do 0 equals x squared minus 3x plus 2, okay? So in order to find x-intercepts, you let y equals 0, and for y-intercepts, you let x equals 0. So in this case, we're letting y equals 0. And to solve this, it is factorable, okay? What multiplies a -3 and adds to 2 would be x minus 2 and x minus 1. -1 and -2 multiply to +2, but they add to -3. And if we use zero product property, I can solve each thing equal to 0. So x minus 2 equals 0 gives me x equals 2. And x minus 1 equals 0 gives me x equals 1. And so I have these two values here. Okay. So then using Rolle's theorem, okay, we can then show that f of 2 is equal to f of 1 because when I plug them in, my both is 0. That's how we solved it, is we let equal 0. So plugging them back in gives me 0. Okay, so by Rolle's theorem, because we're able to make the statement, according to Rolle's theorem, and you have to write these things out when you're using a theorem to kind of prove a point, and the AP test likes you to write. Use your words to write it out. So there exists a value C value, such that f prime of C is equal to 0. Okay, and we can actually find, so it just asks to find the two intercepts and then show that at some point between, we can find that point too. So if we do that, we can do f prime of x is equal to 2x minus 3, and that is going to be equal to 0 at add 3 to both sides, divide by 2, at x equals 3 halves, which is somewhere in between 2 and 1. Okay, it's 1.5, and so that works. It's supposed to be in between it. So this is where your horizontal tangent exists, okay? But Rolle's theorem basically said, since we did this, there has to be this, okay? And we found exactly where that was. Another theorem we're going to talk about is the mean value theorem. Okay, mean thinking like average. Okay, all right, so if we have f being continuous on the closed interval and differential on the open interval, AB, then there must exist a number c in the domain such that my first derivative is actually equal to f of b minus f of a over b minus a, which this side is just your standard slope from algebra 1. F of b is a y value, f of a is a y value, so it's y minus y over x minus x. Okay, so it's outputs and inputs. Essentially, we know that f prime of c is the slope of our tangent. So all this is saying is mean value theorem says that slope is equal to slope. So you're finding the slope of your tangent line equal to the slope between 2 points. That's what you're going to be looking at for the mean value theorem. So it should be easy to memorize slope equal to slope if you think of your calculus slope as the first derivative and your algebraic slope as your rise over run, or change in y over change in x. All right, so for f of x equals 5 minus 4 over x, we're going to find all the c values in the open interval 1, 4, such that f prime of c is equal to f of 4 minus f of 1 all over 4 minus 1. And they technically didn't have to give us this. We could do this problem without all of this, because that would be our first thing, is we would set up our slope. And they told us our endpoints, so we'd use those for our slope. But they kind of gave us that helpful piece of information, so we'll go ahead and use it. So if you're asked to do a problem like this and they didn't set it up for you, you're still going to do f prime equal to plug in one endpoint minus plug in the other endpoint divided by the difference of those endpoints. Okay, so you're doing, this side is the instantaneous velocity, for lack of a better words, and this is your average velocity. So when is your instantaneous equal to your average is what you're trying to find. So let's do the slope side first. So if I go and I plug in 4, I'm going to have 5 minus 4 over 4. So that's 5 minus 1. And 5 minus 1 is 4. And then f of 1 is 5 minus 4 over 1. So 5 minus 4, so 1. And then all over 4 minus 1. And so I have 3 over 3. And so I have 1. So then I'm going to take my first derivative. Okay. What I would do is I would rewrite this here, this part here, as 4x to the negative 1. So that when I take that derivative, it's a little easier to do. So the derivative of 5 is 0. I'm not going to write it. And then when we do the derivative of 4 over x, or 4x to the negative 1, I'll multiply in front. So I'll have 0 minus negative 4x to the negative 2. Okay, so you subtract 1 from the exponent, just like we've been doing. I'll simplify that a little bit to be 4 over x squared, still equal to 1. I would solve this by thinking of 1 as a fraction of 1 over 1 and cross-multiplying and solving. So that I have 4 equals 2x squared, and I will square root both sides. Remember, when you square root both sides, you have plus or minus. So I will have x is equal to positive and negative 2. Now, you have to have a c value in this interval. So the negative 2 is not in the interval. So I will just have c equaling the positive 2, because that 2 is in the interval. Negative 2 is not in the interval. So my answer is just that single value, c. So you're still doing the first derivative is equal to your slope. When you use your slope, if they don't set it up for you, you will use that value to be your inputs. Last example. 2 stationary patrol cars equipped with radar are 5 miles apart on a highway, as shown in the figure. I copied the figure down there for you. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. We're going to prove that the truck must have exceeded the speed limit of 55 miles per hour at some point during that 4 minutes where he's in between them. So when he wasn't being seen by radar, he must have been speeding, is what they're saying. Okay, so what we're going to do is we are going to have an initial position. Okay, so we will do S of t will be our position at time t, and we'll allow that to happen. So S of 0 means no time has passed. So that's our initial position. And our initial position is going to be 0. Okay, we'll just say that this will be our starting point here where t is 0. So our position will also be 0. That makes sense. So that we can calculate as it's passed. So then we have to figure out 5 miles later for the final position. When is that going to be? Okay, so it said, did it say 5 miles? Yeah, so our 5 miles apart. So from one tracking to the other tracking, 5 miles has happened in that instant. And so we are going to have some sort of position of 5, but what in fact did we plug in to get that? So everything is per hour, per hour, per hour. And we're going to talk about it, but only 4, what did it say, 4 minutes? Only 4 minutes has happened after 4 minutes. Yeah, there it is. And so we need to think of 4 minutes in terms of hours. So 4 minutes in terms of hours is 1/15 of an hour. So I'm going to be plugging in 1/15. So at time is 0, our position is 0. At time is 1/15 of an hour, it's been position of 5 miles. And what we're going to do is show that the average velocity, okay, is greater than 55 miles per hour. That's what we want to look at. And so think of average velocity as that f of b minus f of a over over b minus a that we used in the mean value theorem. So what I'm going to do is for my average velocity, we are going to do my output minus my output over my input minus my input. Okay, so that I get 5 over 1/15. And 5 times 15 is 75 miles per hour, which means his average speed was 75 miles per hour. Therefore, he must be going, obviously his average velocity is. So the MVP says that he must have been traveling 75 miles per hour at least one time. So mean value theorem, they call it MVT very often, says that the truck went at least 75 miles per hour. Okay, or he definitely hit that 75 miles per hour minimum one time. Well, I guess it would have been 2 times because we sped up past that and he decreased. But the MVT is saying that instantaneous velocity, his instantaneous velocity would have been at least 75 one time. Okay, is what the MVT is saying too. And so we used average velocity comparing it to our actual instantaneous velocity. Even though we don't have a function, we can still consider, oh, no, I didn't mean to write F, I meant to write S. Our instantaneous velocity be S prime of t, and that it was 75 at least once, at least one time. Okay, that is it for notes today. I know they're not very long, but most of it is old stuff. It's just a matter of combining your first derivative and your slope and putting it together. There might be a couple more examples in the textbook if you want to reference them, but it might just help to kind of get started and work on some of these problems. All right. If you have any questions, make sure you contact me.